let's... okay. Okie doke. So... okay, so for today, so this is the grad session. This I forgot to mention to everybody that they can just go to the same link, and I'll put this link up live all the time, so you can, if you want to log in and stream the 8 o'clock session, you should be able to do that. So so the plan today is to, it's always a little backwards on Fridays because I talk about the grad session first, and then I go to the main session, and sometimes the main session is a prerequisite for the grad session, and so unfortunately that's the way it is today. So I'm going to talk about stuff that will, some of the basis for which will then be explained in the second session. So what I'm doing today is to look at how you can write out the Bloch equation as a matrix equation. So if you're doing something in MATLAB, like say a Bloch equation simulation in MATLAB, for instance, say you wanted to figure out how what the contrast in a particular sequence was going to be, then you might want to do a full Bloch equation simulation rather than just taking out the individual parts. This might especially be the case if you've got a very complicated sequence, a bunch of things are happening. If you tried to do it just by writing the equations out, it would be painful because how many times you'd have to substitute things in. And so the reason for this is the kind of the method you would do if you were actually trying to do a kind of a real world simulation of the Bloch equation. So a lot of what's today is just looking at how you sort of go back and forth between this vector equation, which implicitly has multiple dimensions in it, and then a matrix version of that equation that's written out explicitly, so you can see all the numbers. So if we start, we'll start with with just precession. So how would we write out the matrix version of the Bloch equation that just explains the precession part? So for that, what we're doing is we have just a b0 that's in the z direction, and it's fixed, and then we have our some m vector, and the m vector is precessing around, and then here's our dm dt. So this is our b0, which is there's our m, and there's our dm dt. So if we write out the standard Bloch equation, it's just dm dt equals start off with the m vector cross product with the b vector, and this is just actually b0 vector because there's no RF applied, and there's no relaxation, so just the precession part. So to write that out, so, and then what we want to write out is, you know, first the equation and then the solution to it. So I didn't actually talk about how you derive the solution to it. I'll just write it out. We won't go over exactly how we got it. So let's put it a little bit further over to the left so I make sure I have enough room. Let's go right there. Okay. So here's the first term, dm dt. Now, since that's a vector, what is that actually? How could we rewrite that out as a matrix? So we could write that out as a matrix as a column vector. So that would be the x component, and then the y component, and then the z component. So that's just a 3-number column vector. And so now we're going to write this out as an actual sort of matrix operation. So we're going to write out the cross product as a matrix operation. And you might remember that when we were looking at how you would do that, let's see, so equals that matrix, so I've got about to here, okay. So we wrote out, A cross B to write that out as a matrix operation, so a matrix times a vector. So it's always important to sort of keep in mind the overall picture. So the overall picture is that's a vector, and then it's going to be equal to a matrix times a vector. And when you multiply a vector, a column vector times a matrix, you get another vector. So the output is a vector. So basically vector equals matrix times vector. So we wrote out the cross product like that. And what it looked like was this, strange matrix got 0 minus bz, minus bz, by, and then not minus bz, a 0 down the diagonal, and then a minus by, which is the opposite of this, not minus by, and then finally a minus bx, a not minus bx, and a 0. Okay, so 9 numbers. And then we're multiplying that by the vector that we're operating is the a vector. So here's ax. I always tend to say ay, ac. So that was the set of multiplications that we do to calculate the cross product vector. So this is, the cross product vector, which is the thing that's like dm dt. So that C vector is A cross B, and that's this B matrix multiplied by the A vector. So that's what we're going to do over here. But we're going to make the following assumption, which is that we only have the Z component of B0. So the B, so let's write that out explicitly. So B, so here's the B vector, this guy, but that just equals B0, which just equals BZ. Okay, so that means that the X and the Y component of the B vector are zeroed. So here's the X component here, and there's the Y component. So those guys will all be zeroed. So that's why you get this. That's why you end up with this this matrix that looks like the following. So it looks like 0, and then the gyromagnetic ratio times the strength of the B0 field, which is just the BZ component here, just this guy. And then we're going to have a minus gamma times B0 over here, and then everything else 0. So 0, 0, 0, 0, 0, 0. And then we're operating that on the M vector. So A is the M vector. So there's the M vector. So that's just the X component of the M vector, Y component, and Z component. So all we've done here is we've just rewritten this. Rewritten this equation. So we haven't actually added anything, strictly just notation. So dm vector dt, we spread that out into 3 components, and then we write it out as a matrix that's operating on the M vector. The M vector is A, and the B0 is B, that sort of gets turned into a matrix when we're doing our cross product. Okay, so now, so this is the differential equation. So that's differential equation. So now what we want to do is, it's all on the board, it's good. So what we want to do is solve the differential equation. So we're not going to say how we did that. I'm just going to write it down. So here's the solution to the differential equation. So the differential equation says, for a very small amount of time, this is the update vector for the M vector. But what we want to know is, what about 1.3 seconds? What's the value going to be at 1.3 seconds? And so that's what the solution is. And so the solution is also a vector. So the solution vector is basically the value of the x component at time t and the y component at time t and the z component at time t. So we can put in any old t in there, and then we can calculate what. So that's equal to the M vector at a point in time. So all I've done is just written out the components of the M vector. And so what is the solution? Well, the solution is what we would call a rotation matrix. And in the main section, I'll go over what a matrix looks like that will rotate around the principal axes, and then also what you need to rotate around some arbitrary axis. But what that rotation matrix looks like is cosine of omega 0 t, we'll say what that is in a second, and minus sine omega 0 t, and then sine omega 0 t, cosine 0 t, and then 0, 0, 0, 0, 1. So that's the solution matrix, which turns out to be a rotation matrix around the z-axis. And then what is it rotating? So just like in the case of the solution to T2, when we went over like what was the solution to T2, that was like the magnetization in the XY axis divided by T2. That was so whatever the magnetization is at a particular point in time, divided by T2, that was the differential equation. But when we solved it, we ended up with whatever the starting condition was, the starting T2 condition times e to the minus t over T2. So here's the starting condition. So we have a starting condition here too. So this is the x component of whatever the magnetization was. And the y component of whatever the magnetization was when you started, and the z component of whatever it was when you started. So, and that's what this, so this guy is a vector, and the matrix is going to do something to the vector. And what can a matrix do to a vector? It can basically rotate it or shrink or grow it. This is a special matrix that has the property that it only rotates. It doesn't cause any change in length. That's what the meaning of a rotation matrix is. So it's going to take this starting vector of magnetization and just rotate it. And what is it going to rotate it by? So what angle will it rotate it by? Well, if you look at this thing here, we should say, like, what is this thing here? That's basically just equivalent to the B0 frequency. That's just that very first equation that we went over, which said that the precession frequency equals the gyromagnetic constant times the strength of the B0 field. So this is, you have cosine of two things, but what are these two things? So one of the things is the frequency. So that's the frequency in radians per second. So that's radians per second. Remember, a radian is just like radius 1. So radius 1. If you just go one along the circumference, that's a radian. So the angle that you get from going a distance 1 around a circumference of a radius 1 circle, that's a radian. So that's what that omega 0 is. It's like radians per second. So that's this guy. And then it's multiplied by time. And what's time? Well, time is seconds. So there's time. So I'm just to make sure everything is just completely explicit. And so what do we get? We just get radians, which is an angle. So we're plugging in the cosine of an angle in radians there. So when you're in MATLAB, make sure that you don't get confused. In the zero part of the homework 0, I had some examples of how to take cosines. So sometimes you want to take a cosine of degrees, and there's a function in MATLAB to take a cosine when the argument is in degrees. This argument is in radians, and so the cosine normally, like in programs, in math software, if you don't put anything in, the default is to assume that the argument of a cosine is in radians, not in degrees. But to turn it into degrees, you just got to multiply by 2 pi. So divide by you have to scale by 180 over 2 pi. But in any case, this thing is an angle, so this is just cosine of an angle. And so what this means is at some later instant in time, like 1.2 seconds, you plug in 1.2 here, and then you multiply that by the frequency, like which could be, if you do it in cycles, it would be 130 million cycles per second, and then you get an angle out of that, and then you take the cosine of it. And then when you do this multiplication here, what you're doing is you're effectively rotating the starting magnetization vector. So what does that look like? So let me see what space I've got available to me. I'll do it down here. So what is this doing? So what it's doing is, you can think of it as you've got some coordinate system here. So here's our coordinate system, and we've got the magnetization, our initial magnetization vector here. So this isn't M now, this is M vector, the magnetization vector, wherever the magnetization vector ended up right after the RF got turned off. And so what this equation says is the magnetization vector at a particular point in time is going to be equal to this matrix operating on this starting point vector. And what can this matrix do? The only thing it can do is basically rotate around the z-axis. So here's the z-axis, and there's the x-axis sort of sticking out at us, and there's the y-axis. So the only thing it can do is rotate around. So if we assume, let's just for this particular drawing, that that this m0 plus vector is just is just in the y direction. It's off the xy plane, but it's just pointing in the y direction. So basically, it's going to be precessing around here. And so what is this rotation matrix? This guy is a rotation matrix that rotates around the z-axis. So you can think of it as, you put in an angle. So remember, omega 0 is cycles per second, radians per second times seconds equals radians. So you put in an angle into that matrix operator. And so this guy's a matrix. And what does it do? It just rotates the vector around the z-axis without changing its length. And so where might it end up? Well, let's just say it just ended up, sort of over here. So what is that vector now? That's basically just our result. That's the MT vector. And how did it get there? The rotation matrix put it there. So here's this guy. That guy was done by the so the R matrix Z omega 0 t did this. So the way this equation works is, for any time, so if you want to calculate a whole bunch of time points, what you do is for each time point, you start from the very start, and then you multiply it by the matrix with a certain setting of time in here, and that will rotate to this point, and the next time point, you just do it again, it rotates a little bit further, and then it keeps going around. So that's that's the solution to the precession part. So we end up kind of, compressing our notation down to, the m vector at a point in time just equals this rotation matrix operating on whatever the initial condition was. So, so we didn't do anything. We didn't sort of do anything useful except just write out the solution to the, well, we did something useful. We told us what this, the actual solution to this differential equation was, written out in matrix form. So, okay, so that's just precession. So that was the differential equation. And then the solution to it, written out in matrix form just for precession. So there's no, there was no, there it is. Yeah, so there was no relaxation in there at all. Okay, so now, what about relaxation? Well, it turns out you can tack in the other parts of the Bloch equation into a single matrix. So you just have a nice all-in-one matrix that includes the precession plus the T1 decay plus the T2 decay. It doesn't include excitation yet, so we can add that in also, because obviously we need to be able to, the B vector in the Bloch equation can be affected by, it's affected by the B0 field, but the gradients might be on. That changes the B0 field up and down as you move in space. And then the RF might be on. That also changes the B0 field. So all of them should have to be in there. So now the plan is to include the, there we go, include the relaxation in here. So what is the relaxation? Well, there's two parts of it. So one part of it is it makes the vector go toward, the center here. So here's the z-axis sticking out, and we'll make it sort of dotted as it goes. Yeah, so it aims toward the center. That's the T2 decay part. And then, so it makes it smaller in the xy direction. And then it makes it longer, or makes it more positive, because it might have been negative to start off with. It makes it more positive in the z direction. So, but that's all just going to be additions to this current magnetization vector, current m vector. So if here's our initial Bloch equation without the other two terms, now we want to put the whole Bloch equation. So the whole Bloch equation, don't go off. So the whole Bloch equation is got those other terms in it, and so that equals the m vector crossed with the b vector. That's the part we just did. That's the first term, and then got the T2 decay minus the the x component times the unit vector plus the y component times the unit vector in the y direction. So that's just, that guy is just the vector sum. So like if you did it in 2 dimensions, it would just be, the x component and the y component gives you that vector. So there's the, like mx and y. Turned into vectors by multiplying times the unit vectors divided by T2. And sometimes we just said, we just skipped all that mess and we just said, what we're talking about is the length of the m vector in the xy direction. So the first one, and then we also subtract off the second, more complicated one. And that one was the starting magnetization. Sorry, not the starting magnetization. The current value of the Z magnetization minus the equilibrium value. So that's just a constant. That's just whatever whatever you get to after you've been in the magnet a long time, and that's not changed. That one doesn't change. That's just a known value, and that whole thing, multiplied by the k, the unit vector in the z direction in order to turn it into a vector, divided by t1. And so what we want to do now is just embed all that crap into this matrix here, and just see how it comes out when we find the solution to it. Because remember, the solution was what we did in the previous class. So in this case, we've got a not much more complicated starting point. So the starting point is just tack in the decay terms. And so if you have a matrix along the diagonal, you have the numbers that essentially tell you what the scaling of the effect of operating that matrix on a vector is. The scaling in the x, y, and z direction. So the way that this matrix gets modified is maybe I'll draw it down closer to the same height so that it's so you see the parallelism. So here's but I got to go up because this is in the way, and I want to leave that up there because that's useful. So we'll just put it up here. So here's the same thing we did before. So I won't write it out. It's just the x, y, and z component of the update vector. And now we've got some decay terms in there. And so the decay terms are 1 over t2, and again 1 over t2 because we have sort of the x and y parts of that. And then minus 1 over v2 over t2, and then minus 1 over t1 for the z. And then the other things are the same way they were before. So here's the precession part, and we've got a negative version of that over here, and then 0, 0, 0, 0. Okay, so now what we've done is we've basically just built in all of these things. We haven't got to where you get the minus part. So now we're operating on the same vector we were operating on before, which is the whatever the current state of the magnetization is, the XYZ components of that. But now we have to sort of deal with that constant. And so the way we deal with that constant is we add on another vector. And that this vector is 0, 0, and then the mz 0 over t1. So we just pulled out this guy. And it's a plus because we got sort of a minus minus. Okay, so so all we've done now is just written out. So that's how to write out the Bloch equation in a matrix that includes all the actual components. So then we have to have to solve this. And so when we solve it, the whole thing, we're going to get sort of a mixture of this matrix, which does the precession, plus the solutions that we wrote down separately for the T2 decay and the T1 decay. And so what does that look like? So this guy was the differential equation, and so what we're writing down here is the solution. So now we have like an all-in-one solution that includes the precession plus T1 plus T2, so we can calculate what the length and direction of the m vector is at any arbitrary point later in time. So what that is equal to is, so here's the mt. I won't spread it out into its components there. We'll just assume that it's just like the other side. Okay, and so now the solution to this now has two matrices in it. So the first one has the decay part. So here's e to the minus t over t2 down the diagonal, e minus t over t2. That looks like the solutions that we figured out for this part. And then here's e to the minus t over t1. And then the rest is 0, 0, 0, 0, 0, 0, 0, 0. There's the 9 numbers. Okay, so that matrix is basically just going to, so if that operates on a vector, that would just scale a vector. So this is what a matrix looks like when it just rotates a vector. This is what a matrix looks like when it just scales a vector. It doesn't it doesn't rotate it. And so this is going to scale a vector, and so then we have to multiply it by a vector. But the vector we're multiplying it by is going to be this rotation operation. So now we just have the whole rotation operation in there. So what is that? So that is, cosine omega 0t, same as before. Sine omega 0t, 0 minus sine omega 0t, cosine again, not minus omega 0t, 0, and then 0, 0, 1. Okay, so there's that guy, and then that guy is going to be operating on the starting magnetization like before. So here's mz, the z component, it's the x component of the starting magnetization, whatever that was. That's this guy right here. Mx at the starting point in time, my, mz at the starting point in time. Okay, and here's a bigger parentheses. So what's going on here? So this is the rotation matrix. It's operating on a vector. What is it? What is the output of that? So this is matrix times vector. So the output is vector. So the output is vector. So this whole thing is a vector, and then we have another matrix operating on it. So that's another matrix. So there's another matrix over here. So that matrix is operating on this vector, and then you get another vector. So just always. So later on, what happens after you get good at this, you don't write all the parts out. You just have a letter for this kind of letter for this guy. But then in your mind, you realize, well, that guy went the matrix, and so when I do something to this guy, which is a vector, and then I get a vector. Okay, so now you'll get something different if you multiply a row vector times a column vector, but here we're multiplying a matrix times a column vector, and that will give you a vector, just a single vector. Okay, so that is almost done, but then we have to deal with this guy, and so what that guy turns into is another column vector. Draw it the same size. So this guy is just turns into 0, 0, and then kind of a big mess. So the mz at the 0 at the time just after the starting condition times 1 minus e to the minus t over t1. So that's just 3 numbers. So again, this is our initial condition. So this matrix setup is capable of basically you can start. So what's the use of this? So basically, you can just take any old starting vector. So for instance, you could have one that was like going down. So like here's the plane, that's the plane. So you could have one that's actually sort of pointing downward at any arbitrary angle. It could be any arbitrary angle along that axis, any arbitrary angle along that axis. And then if you know what the T2, this is assuming you know what the T2 and the T1 is, you can then predict exactly what's going to happen to this at any point in time. So you could make an animation just by going through all these doing this calculation for each point in time, and then it would show you exactly how that vector would evolve over time. So they would do all the, it would do all the, the spinning around the axis, and then the shrinking down really, really small, and then expanding up to the eventual mz0. So this is how you would sort of practically calculate that trajectory. Okay, so in the last 5 minutes, we still got 5 minutes left. So how could we also tack in the excitation? So the excitation is going to be some kind of rapid wobbling in the xy axis of the B field. So it turns out where that gets tacked in, there's still a few zeros left in there, and so you can see so what is if we go back to our original sort of cross product matrix, what are the zeros? Well, the zeros are this is the B vector, and the B vector is this is this B here, that B vector there, and so it's the y and the x component of the B vector, and we were assuming in this derivation here, and also in this one, that the x and the y component were 0 because there was no B1 field. So these guys are 0 here, and so there's just enough numbers in the matrix to put in the x and y component of the B1, and so that's where it would go. So it would just basically go into here, and so I got that up there. I'll just draw it underneath this one. So what we're going to do is where would we stick it? What does it look like to stick in the excitation? But I'll leave out the T1 and T2 just to make it a little bit easier to draw. And I'll just draw this one. And so we pretty much have the same, and we're not drawing the solution. We're just drawing the differential equation. So this is differential equation, include excitation. So excitation and precession. And ignore T1, T2. Just for clarity. So this is the differential equation, but now including excitation. So the excitation's actually in this equation right here already. We just we weren't sort of thinking about it, but this includes the B0, but it also includes the B1. That's the excitation, and it also includes the gradients, because the gradients affect the B0. So, sorry, not that guy. The B. Okay. So this guy here, includes B0. But it also includes B1 if we've got it turned on, and it also includes the gradients if we got those turned on, because those change the B0, add to the B0. So what does that equation look like? So that equation basically, that matrix basically looks like this one. So it still has this part of the matrix minus omega 0. Omega 0 is the same thing as gyromagnetic ratio times B0. So that part is still there. And now the additional parts are, we just have to mess with these guys, the B meaning B over here, the X and Y components of this guy, which is the B1. And so what does that look like? So that looks like we got a frequency of the B1 field, that's what the 1 is for, at a particular time. So the frequency can change at different times, multiplied by where it is around the circle. And then we have the same thing over here, cosine, and you get, there's a minus down here. The minus is because we're going clockwise. If you look at the top, we're sort of like, we're moving around in a clockwise direction. So you might expect, if you look at this thing, for the by to be positive, but the by is negative because we're going clockwise. Times sine omega 0t. And then this guy, I'll put it slightly under cosine omega 0t, and then finally 0. So there's the diagonal. There's our matrix. Just make sure you can see the matrix. Okay. And then just times, whatever the magnetization currently is. So this is the differential equation including this is how you would stick the B1 field into the differential equation. And we could also tack this, and we could essentially do the same thing over here and have that matrix all filled out. So that would be the final insult. So that would be how you would calculate how this vector changes when you turn on the RF also. So you turn the RF on. It's a wiggling RF, rapidly wiggling RF. And decay is occurring the whole time. So like you could turn the RF on for a long time, but there's going to be changes due to the RF, and there's going to be changes due to the decay, changes due to precession. So that would be everything. So I didn't write out the solution to it, but that's actually somewhat harder to get. But this finally shows you how you can sort of add everything in and sort of simulate the whole mess. Okay, so any questions on that mess? So this, like I said, you wouldn't do this by yourself. There's software out there that can implement this for you, but it's worthwhile sort of getting some idea of what the software is doing. You wouldn't have to actually sort of write out these simulations. There's block equation simulators in MATLAB out there, but this is what they're doing. Okay, so that's that's this part. And so David, could we end the recording now?